My today talk will be devoted to nonlinear chiral metaphotonics. So here's the outline of my talk. So firstly, I'll just briefly we'll do some introduction to this area, and we'll discuss some recent results in our group devoted to chiral nonlinear metaphotonics. So yeah, we'll start from introduction. So basically, there are three main words: nonlinear chiral and metaphotonics, and I'll introduce uh, three of them like one by one. So we will start from nonlinear. So what is nonlinear? So if we have just linear case and in linear optics, then the light interacts with um, some matter. So in linear case, it's linearly dependent on the material polarization linearly depends on external electrical field. That meaning that the electron of the media oscillating with the frequency of the excitation wavelengths. However, if we have the powerful source such as laser, so then we'll have next nonlinear terms like second order nonlinearity and third order nonlinearity. These guys here they are related to the nonlinear processes. So, and one of the nonlinear processes is harmonic generation, and harmonic generation have many different applications. So, for example, it can be used for laser industry to generate certain frequencies, as well as for biological imaging and material characterization. So the canonical example of the harmonic generation is the second harmonic generation and the third harmonic generation. Basically, the third harmonic generation is then we have the material with second order nonlinearity and pump it with laser, generating double light with double frequency. And for third harmonic, it's the same process but with free photons. And those processes they are really depend on the symmetry of the crystals. So for non-center symmetrical material, for center symmetrical material, because of the symmetry and the harmonic potential of the material, the even harmonic is not allowed. For non-symmetrical material, then the symmetry is broken and electron can oscillate with our frequencies, so we can observe second and fourth harmonics. So next we'll talk about chiral. So what is chiral means? So the actual chirality was introduced by Lord Kelvin. So this is a direct quotation. So I'll call any geometrical figure or group of points chiral and say that it has chirality if its image in a plane mirror ideally realized cannot be brought to coincide with itself. So like on simple language, it means that the object called chiral, geometric chiral, if it doesn't have any mirror symmetry. So from this perspective, a sphere is ideally a chiral object because it's have like infinite mirror symmetries plates, and the helix is a chiral object. So there are many chiral objects in the nature around us. So, for example, our hands are chiral, and some of the molecules have the chiral isomers. So, one of the such examples is glucose, which is kind of like simply sugar. So there is a D-glucose, which is quite known, and we eat it every day. But there is also L-glucose, which is basically chiral copy of the D-glucose. And fun fact that they actually both of them sweet because they interact with our receptors, but this one can't be digested. So basically, if we eat this one, so it will be sweet, but it will be zero calories. So there actually was a real idea to create a sweetener based on this L-glucose, but it ended up it's like too expensive because nowadays like there's much more cheaper and easy to produce in sweeteners. So um, uh, that was like geometric chirality. So the optical chirality is meaning that the light, so the object will differently interact with right circle polarized light and left circle polarized light. So the same molecule of the glucose, in the solution, it will be differently interact with left and right polarized light. So if we have a solution of sugar and put it there, so if we have a solution of sugar, so the LCP light and RCP light will have a different transmission. So, but in the nature, such material has quite low chiral response. To overcome this, we need to create new materials like artificial materials, metamaterials. So that's how we come to metaphotonics. So basically, metaphotonics is take roots to metamaterials. So metamaterials. So original idea of metamaterials originate from the overcome the Snell's law. So everyone knows Snell law. So then we have like two media with different refractive index, and the beam passed through the media, it will be refract. So and people was thinking, what if they have negative refractive index, which is not possible in nature, and there was there was some such work some time ago. Then they create the artificial material, which is called metamaterials, based on the split rings. And in fact, indeed, in this material, the electromagnetic wave can refract in different direction because of the negative refractive index. And now a way to control the optical properties is creation, like it's a single particle supporting mirror resonances. So mirror resonances, it's there's certain type of resonances. If we have the particle which is we have wavelengths comparable to the size of the particle, will have like mirror resonances. There is such particle can maintain two type of resonance: electrical resonance, electric dipole resonance, and magnetic dipole resonances. So in optics, that means that at these resonances they will scatter it with different wavelengths. And another thing about the mirror resonances, that they actually can localize electrical magnetic field. So there's one example there people create plasma between two grapes, which is mirror resonant, and they just put it in microwave. And because of like significant localization of electrical field, they obtain plasma between the two grapes. So yeah, so the one particle have a one local resonance. However, if we put like several of them, they might become overlap each other, and they become respond as one solid media, which is one, like they respond collectively. So that is a metasurface, and metasurfaces can be used for many other for many applications like spectral control, harmonic generation, control of polarization, or like meta lenses or light routing on all the many hours. So among these resonances, which among the resonances that can be supported by the metasurface, there's one which was discovered relatively recently. So it's called Baustein continuum. Basically, every periodic structure can support this resonance. But this resonance, it's actually originated from the destructive interference. So it can't be excited. It has infinity quality factor and can't be excited. So to reach this resonance and excited, we have to break the symmetry, and then it becomes a quasi-Bessie quasi-Band-standing continuum mode. So there are like several many other actually ways to how to achieve it. So we have to break this symmetry to achieve the reachable quality factors. So basically, the idea of nonlinear chiral metaphotonics, it's utilize the metasurfaces for controlling chiral harmonic generation. There was some early work in the beginning of this century, so for studying nonlinear chiral response. But first of the work, they were in plasmonics, and mostly they originated from not from resonance, but mostly from imperfections. For example, this one, I will show that that's like symmetrically, it's not possible to have a chiral response here, but they did observe it. And later, the development of this area, there was some work in plasmonics, but exploiting symmetry. And after some time, there was one of the first work which used the bound-standing continuum and dielectric metasurfaces for achieving chiral harmonic generation. So there are like couple ways how we can determine how we can measure or determine like chiral effects. One of them is so-called dichroism. So imagine we have metasurfaces here, and we pump it with we eliminate it with R component, and then we separate R component and L component in the transmission, and vice versa for. And the same is for L component. Then the CD which is so-called dichroism, will be just the difference between L component and R component divided by the sum. And for nonlinear case, it's almost the same, but here instead of the transmission, we have intensity of the harmonic. So, and for as I said, the symmetry is quite important for harmonic generation. So, for example, if we have this like L-shaped meta-atom, and it does have mirror symmetry, then the both like linear and non-linear CD will be equal to 0. However, if we slightly if we will be shifting this square, and this meta-atom become achiral because there is no mirror in plane mirror symmetry, and the both linear and non-linear CD are possible in this time at this case. When we reach the middle, so they become like T-shape. So it's again we have one mirror symmetry, and the CD, both CD linear and non-linear becomes 0 because we have like presence of the mirror symmetry, and then we reach another edge of this rectangular. We have like switch of the CD, and this is how we can control in-plane symmetry. But there are also out-of-plane symmetry. So basically, if we have a metasurface without a substrate, so in this case, because we do have out-of-plane mirror symmetry, so the CD linear CD will be 0, but non-linear CD is not necessarily 0. So this one can be easily break by just adding the substrate. So then we add the substrate, both linear and nonlinear CD can be not 0. Yeah. So yeah, after this introduction, I'm going to some recent results. So first one will be devoted to nonlinear chiral metasurface based on van der Waals materials. So as I mentioned before, so there's like resonance which is called like BIC mode. So and then it's like true BIC mode. Um, it's impossible to excite it. So we have to break a symmetry a bit. Then this mode will be reachable, but because of the mirror symmetry here, it's still not applicable for chiral purposes. So then we need to introduce the small degree, which is break the mirror symmetry and become and enables the nonlinear chiral response. So here the concept. So we have this metasurface made of the HBN with these certain meta atoms, which will differently interact with left and right circle polarized light. Yeah, so we firstly linearly characterize it. So this one simulation. So they see nice and clear mode here, which is quasi BIC mode, and yeah, so we see significant localization of electrical fields, and and in the experiment they observe quite similar behavior, um, but except the lower quality factor of the resonance. So next we study the nonlinear response for this metasurface, and we first did simulation for harmonic duration. So as you can see here, the right component more pronounced than the rest. So if we estimate circle of CD, nonlinear CD as according to the formula I show you, and they are shown here. So at the vicinity resonance, there will be some pronouns of the CD, and next so from theory we expect to see some nonlinear circle dichroism around the resonance, and next we measure third harmonic from this metasurface. So basically this one just ferromonic spectra, and it's usually how it's look around resonance. So it's can be visible in dark room, and we measure power differences, which confirm they have third order nonlinearity. And then next we integrate this signal for different pump valences and observe the enhancement of the absorb the enhancement of the ferromonic around the resonances, which is expected due to the significant localization of electrical field. And then they calculate the circle dichroism. It's actually quite similar to that what they theoretically expect. And for just reference membrane, it's around. I mean, for the reference HBN film, it's just around the zero. So, and the next project is devoted to chiral metasurfaces with monoclinic lattices, or monoclinic lattices of the achiral meta atoms. So, if we want to create a metasurface made of the simple meta atoms, like let's say cylinders, which is like fully achiral. So, and we want to use this square lattice. It is not possible to achieve it because again mirrors to mirror symmetry here. But if we just make this lattice monoclinic instead of the rectangular, we actually break the implant symmetry, and the chiral response become chiral response is possible in this case. So that was the idea for this project. So we basically we have these cylindrical silicon cylinders on the glass substrate. So here's the metasurface, and we did this with monoclinic lattice. Um, yeah. So basically, from linear spectra, we have like two modes, which is also pronounced, also visible on the experimental curves. And linear here is measured and simulated linear CD. So yeah, next we turn the nonlinear CD, also the measured harmonic duration again, and here this the um integrated power of harmonic duration for different pump valences. As this one is theory, this one experiment, so they match quite well. And the interesting thing here that if we just flip the metasurface and we'll pump it from the opposite side because we change the symmetry, the the linear response will be just flipped. I mean, it will be the same, but change the sign. But for nonlinear, it will be not that simple. So it won't be just flipped. It's a bit more complicated here. But again, like they match quite well the theory and experiments here. Um, so on the third part, I will talk about harmonic generation from resonant membrane metasurfaces. Um, so as I told you before, that if we have a membrane, um, if we have a metasurface without a substrate, the linear CD will be zero, while the non-linear CD is not possible. It could be not zero, and that's exactly what we want to achieve in this project. So basically, we developed a freestanding membrane without a substrate, and and pump it in. And we want to observe that the weak linear CD because of the symmetry and strong non-linear CD. So one more important thing here that actually there is harmonic selection rules depend on the rotational symmetry of the metasurfaces. So basically, in this case, we use C4 symmetry. So C4 symmetry means for harmonic generation, that means that we won't have a copolarized component due to the symmetry. So that will be only cross-polarized component. Yeah, so we have two type of the structures. One of the structure with fully C4 symmetrical, and in our structure we intentionally break the symmetry uh, to yeah just we intentionally break symmetry. I'll show later the result, and the firstly we measure the linear transmission. So ideally, we expect that this copolarized components should be strictly equal to each other, but because of the some of the fabrication issue that actually it's not like fully restraining membrane, there is some gap between the membrane and the membrane and the substrate here. So that's why it's not fully zero. Sorry, not fully equal to each other. But the cross component still like zero because selection rules for selection rules for C4 symmetry, and yeah. So in this case, it's close to each other, close to this case, but the cross polarized component now allowed because we break the symmetry. So we then turn to the harmonic generation again and measure. So we measure all four components. So basically, it's two copolarized components of the harmonics and two cross-polarized components. Then they can integrate the signal, and what this so for fully symmetrical C4 membrane is that clearly the cross-polarized component from left to right is clearly dominant, while the rest is observable but small. So we estimate the nonlinear CD, and which is quite significant and close to -1. Quite expected from the simulation for this structure. And for the structure with broken symmetry, then we intentionally broke the symmetry. So the cross-polarized component is still quite strong, but because of the broken symmetry, we can achieve the copolarized component here, and because of this copolarized component, we can effectively switch the nonlinear CD from negative to positive, which is again have a quite good match with theoretical prediction here. Yeah, I guess the one of the last project I want to show to you, it's again related to the freestanding membranes, but here instead of the plane with symmetry like C4 symmetry in the previous case, here we come up with idea to creation of the meta atom, which is basically elliptical hole in the square lattice. And again, then it's for certain angles when we have mirror symmetries like 0, 45, or 90, the both CDs will be 0 due to the symmetry here. But for the angles between them, we expect to observe strong nonlinear CD. So they firstly characterize them linearly. So for the 0 degree, as it's shown here, so we have the copolarized component and cross-polarized component, they equal to each other because of the symmetry, and the CD is strictly 0. Then we took the two angles, it's basically 23 and 67. So for 23 degree, for both of them, the copolarized transmission is equal to each other because we have out of plane mirror symmetry here. However, for cross-polarized components, they are quite different and swapping between these two angles, and we can achieve positive CD, positive linear CD in this case, and then we're just rotating meta atom. We can achieve the negative CD with the same amplitude. In reality, it's become a bit more complicated. So we did fabricate the sample. It's freestanding membrane, and for this sample, it's ideally freestanding membrane, so there is no substrate at all. So we can blame substrate for this non-zero CD here. So for angle of 0, then they have a mirror symmetry in plane and out plane. The CD is supposed to be around 0, so it's close to 0, but still not 0, I assume, because the ideal structure, these elliptical holes, are not fully symmetrical. But for the 23 degree and for 67 degree, we do see the switching of the linear CD from the positive to negative value. So basically, in the angles in between, we also observe for 45 degree, we observe zero CD due to the symmetry. So basically, we can, by changing this rotation angle, we can control the CD for this system. So, and next we study again for harmonic duration from this such structure. So we recorded all four components for many rotational angles of these ellipses. So here, this map is integrated signal for harmonic for depends on the pump valence and the elliptical rotation angle, which is this one. So basically, we do observe enhancement throughout resonance, and we see that resonance slightly change position with change of this rotation angle of this ellipse. And then then we check the nonlinear CD. So this map is nonlinear CD for this structure. Basically, the blue one means it's negative, red one means it's positive. So they do observe several areas of interest, so especially around the resonance. They see this. Well, first thing we see that around for the angles when we have a mirror and plane symmetry, it's strictly zero. So from like for 0, 45, or 90. But for the angle in the middle and around the resonance, we do see the change of the sign of the nonlinear CD. So if we have a closer look for certain angles, so for 0 degree, for 23 degree, and 67 degree. So for 0 degree, we do observe significant enhancement of the harmonic duration at the resonances. But as you can see, the component close to each other. So the overall CD here is 0. But however, for like 23 degree, the R component is more pronounced than the rest, and the CD is close to 1 around the resonance. And for the opposite angle, which is 67, we have like switching behavior. And in this case, the L component is dominant, and the CD become close to -1. So basically, it's switch of this state to opposite one. And by rotation this angle, in the other angles in between, we can basically tune the nonlinear CD in any value, like any value you want. Yeah, so I guess I'm going to summary of my talk today. So basically, hope I have shown that we can achieve strong enhancement of nonlinear optical response with strong chiral dichroism by the creation of the metasurface. So show that for chiral harmonic duration, it's really important to develop the symmetry of the metasurface, and yeah, hopefully this work they have a new opportunity for compact chiral nonlinear photonic devices for many other applications. So here is the work I mentioned in my talk. This one is a really nice review from our group. And with that, I want to say thank you to all our group members and collaborators from the ANU and worldwide. Um, and thank you for your attention.
Because we are also connected online, so I have to use the microphone. So any other questions? Any questions, please? Yeah.
Thank you for your talk. That was really nice. Could you go back to slide 60 for me, I think?
60.
6T, sorry, right at the end.
Yep.
This one. So this is the experimental realization of the slide before.
Yep.
And in the slide before, you had a difference between the copolarized CD and total CD. Is this the total CD?
This is total CD. Yeah, because the problem here was that to get the copolarized CD, we have to have a water plate in the collection point, in the collection channel, and we was not able to reach it in this setup because it was FTR, and it was a bit, and it was done by our collaborators, but they were not able to distinguish L and R component in the collection. So ideally, we have, well, here we have to, yeah, it's a bit tricky because we won't see these two peaks here, because this one is the like TR. It's basically the sum of TRR plus TRR. So that's a bit tricky to compare them, but the total CD should be should be matched quite well. So we observe like two peaks here and kind of two peaks here.
And here the total CD comes from just the cross-polarized terms.
Yes. Ideally, the copolarized component equal to each other because of the out of plane symmetry.
Right, the out of plane symmetry. Cool. Okay, thank you.
Hi, you alluded at the end to some applications. Could you give me a concrete example of where high order nonlinearities are used in quantum photonics or could be used in quantum photonics?
So I guess high harmonic generation can be used for high harmonic generation. So it can be used for like generating really short pulses. Yeah, and maybe reaching some extremely like ultraviolet ranges. Or I mean, I'm not sure it's quantum. Yeah. Yeah, I'm not sure I have like short example for quantum here. Sorry.
From the fact that nature gives us high order nonlinearities, what are the advantages of going to third or even higher order? I mean, what fundamentally do you get?
What fundamental we get from harmonic?
Or higher order nonlinearities. Nature provides you with material, but is there any sort of fundamental each between order and some understanding material for?
Well, strictly speaking, there is no model describing high harmonic generation from a solid body. That it's quite known for gases and for gases and atoms, but for solid body there is some approximation, but there is no like strict model. So maybe that it will be one of the good fundamental point to study high harmonic gyration, that we can potentially in future build some model for high harmonic gyration from solids.
Thanks. Yeah, Dimitri.
One state continuum forms structures of centers.
Yeah, so this one is not Bunsen continuum, but guess I don't have the plot here, but maybe this example is. So yeah, I guess this one. I guess this one is classical geometry for Bunsen continuum. So basically, it's ideally symmetric, and maybe it's. Yeah, so I guess maybe I can explain it here. So there's like this mode, which is in gamma point resulted from this destructive interference. So basically, it's the same picture, but it's trapped inside these two bars. Yeah, I guess I don't have additional slides here to properly explain it. Sorry.
Yeah, I think maybe it's a quick one. Let me conclude by acknowledging also Dimitri and Marisha for organizing the colloquium and also for carrying to settle everything up for this seminar. And thanks, Pavel, for your talk. And also, please enjoy some afternoon teas if you're around. And I think that will be some chats as well. Thank you.